Welcome to episode 3 of our series on public key infrastructure. In the last 2 episodes, we learned what a man-in-the-middle attack is. We learned how to perform a man-in-the-middle attack using techniques like ARP poisoning and DNS poisoning. In this episode, we are going to learn about encryption. Encryption is a tactic that can help achieve confidentiality, which is one of the 3 goals within the public key infrastructure. The majority of you will know what encryption is, but for the sake of being thorough for this series, I will give a few simple definitions that are well understood even by a non-technical audience. I will talk about both symmetric encryption and asymmetric encryption. To make this lecture interesting, I will demonstrate symmetric encryption and asymmetric encryption in 3 different ways. For each encryption type, I will do one demonstration with visual concepts, one demonstration with basic math formulas, and one demonstration with a computer command line tool called OpenSSL. To make sure we're all on the same page, let's define encryption. Here is a definition from Wikipedia. In cryptography, encryption is the process of transforming information in a way that only authorized parties can decode. This process converts the original representation of the information, known as plain text, into an alternative text known as ciphertext. As an example, on the right is a piece of ciphertext in purple. It has been encrypted to make it difficult for unauthorized people to understand what the original plain text message is. How would we decipher it? There are many types of encryption, and 2 broad categories of encryption are symmetric encryption and asymmetric encryption. Before I give specific definitions of these, let's try to decipher this message using a well-known symmetric encryption process. Let's say your manager gave you the ciphertext QNUUX. To decipher this text, your manager says you need to know 2 things. The first thing you need to know is the step-by-step procedure to follow to decipher the text. And the second thing you need to know is a secret value. Let's start with the procedure. Your manager says the procedure requires shifting alphabet letters around. If that were the case, you might start with a grid like this. Every letter in the alphabet can be represented by a number. A is 0, B is 1, C is 2, all the way to Z is 25. Next, your manager says that you also need to know a secret, and the secret is the number 9. Your manager says to never tell anyone else about this secret number, or else it would compromise the confidentiality of the ciphertext. In other words, anyone can crack the message if they know 9 is the secret value. With this knowledge, what you can try to do is start with the letter Q. You notice the letter Q is associated with the number 16. Then you can take a guess and notice that 16 subtract the secret 9 gives the number 7. You notice that the number 7 is associated with the letter H. So you write down H as the first letter of the original plain text message. You repeat this with the second letter N. 13 subtract 9 is 4. 4 is the letter E. So you write the letter E as the second letter of the original plain text message. At this point, you don't know if your procedure is entirely correct. The only way for you to know if this process is correct is for you to continue and repeat this process for every letter of the ciphertext. If the final plain text message is something intelligible to you, then it probably means you've successfully decrypted the message. Luckily for us, our process is correct, such that if you repeat this process for every letter, you will see that the original plain text message is hello. Congratulations, we just used something called Caesar's cipher to decrypt a message. So then, what is a cipher? A cipher is a series of steps that you can follow to encrypt or decrypt a message. Sometimes you might hear the term algorithm used instead. Caesar's cipher is an example of symmetric encryption. And as to what is symmetric encryption is a form of encryption where you use the same secret for encryption and decryption. You will see later on that in asymmetric encryption, more than one key is used, which is very different from what we just saw with the symmetric encryption in the form of Caesar's cipher. So just remember that with symmetric encryption, we use the same key for encryption and decryption. In the meantime, let's move on. It's well known that computers are great tools for performing mathematical operations. So let's do a quick mathematical demonstration of Caesar's cipher. To encrypt a message, it is the message plus the secret key. To decrypt a message, it is the encrypted message subtract the secret key. As an example, let's say the message is 2490 and the secret key is 15. The encrypted message is 2490 plus 15, which is 2505. To decrypt the encrypted message, you take the encrypted message of 2505 and subtract it by the secret value of 15. And now you can see that the decrypted message is 2490, which is the same as our original message. Caesar's cipher is very weak, so it's not really used in any commercial or practical setting. Caesar's cipher is really used just for educational and illustrative purposes. Here are some ciphers that you may have heard of in practice. The first is AES, which is Advanced Encryption Standard. This one is very popular and you basically hear it used frequently in applications served over the internet. There is also DES and Triple DES, which were very popular at one time, but it is not used as much anymore because of known vulnerabilities. There is also Blowfish, which hasn't officially been cracked, but its security has been deemed insufficient by the NIST standards. Twofish is the successor to Blowfish, and although it is a strong cipher, AES is more performant, and hence AES has generally been more popular than Twofish. There are many other symmetric encryption ciphers that you can explore. I just listed some of the more well-known ones, with AES being the most actively used for internet applications. Let's move on to a practical demonstration of symmetric encryption. If you have a Linux computer, you can follow this OpenSSL example. OpenSSL is a command line tool that comes with most Linux distributions. It provides a lot of useful encryption utilities. So let's do a demonstration. Let's say I write the phrase eating bagels to a new text file called plain.txt. I can use this command to encrypt the contents of plain.txt and save it as a new file called encrypted.txt. This way, if you look at the contents of encrypted.txt, it will be completely unintelligible. Let's take a closer look at each part of this command. The ENC part of this command stands for encryption, so that means you will be accessing OpenSSL's encryption tools. The AES 256 CBC means we will use AES as the symmetric cipher. The 256 means that the symmetric key will be 256 bits long, which means it can be any number in a set of this many numbers. The CBC means cipher block chaining, which is a mode of encryption that I don't need to get into in this video, but just know that CBC mode helps strengthen the overall encryption process. We are also going to supply a password of ABCD. This ABCD will actually be used by OpenSSL to derive the symmetric key used to encrypt our plain text message. And then we will save the output as encrypted.txt. To decrypt the encrypted.txt, we basically run the same command, but this time we pass in the encrypted.txt with the -d option. So let's try this out. I opened up a window to a Linux machine. Let's write eating bagels to a text file. Now let me open up the file just to confirm the contents does indeed say eating bagels. And so far so good. Now let's encrypt plain.txt as encrypted.txt using the AES 256 CBC and the password ABCD. Now if I open up the encrypted.txt, notice that nothing in here is intelligible at all. It's pretty much all scrambled. So let's exit this file. And now let's decrypt encrypted.txt. So I can just run the same command, but instead place in the in file for encrypted.txt and use the -d option. And now you can see that eating bagels is the original message. I can email the encrypted.txt file to a colleague, and as long as they know the password is ABCD, then they too will be able to decrypt the file. Anyone else who does not know the password will not be able to generate the symmetric key needed to decrypt the encrypted.txt file. Now that we understand how symmetric encryption works, we should understand that it has a weakness in typical usage over the internet. The weakness lies in the fact that it is not easy to keep the symmetric key secret. The person you wish to deliver the message to will eventually need a copy of your symmetric key to be able to decrypt your encrypted messages. Let's use this visual aid to demonstrate the problem. Let's say Ali wants to send a message to Boba. Ali can start by creating a secret key for an open lock. Ali places her message into a box and locks the box. Ali then pays the postal service to mail the secret key and the box to Boba. Once Boba receives everything, he can use the secret key to open the box. The problem is that a bad actor could intercept the secret key while the box is in transit and then gain access to the contents of the box. How would you deliver the secret key in a fast and secure way? That is the challenge when using symmetric encryption for internet traffic. When you interact with a website, dozens to hundreds of round trips are made in a short amount of time between your web browser and a web server. If you share the symmetric key along with this data stream, the symmetric key would be exposed to a bad actor who is performing a man-in-the-middle attack. So, although the symmetric encryption is known for being fast and efficient, keeping the symmetric key secret is a challenge. This makes a good transition to an alternative method known as asymmetric encryption. Asymmetric encryption differs from symmetric encryption in that it does not use just one key. Instead, asymmetric encryption uses two different keys for two different processes. Asymmetric encryption uses one key for encrypting the data and a separate mathematically related key for decrypting the data. We call the key for encrypting the data the public key, and we call the key for decrypting the data the private key. As such, asymmetric encryption is also sometimes referred to as public-private key encryption. The public key can be made public because there is nothing secretive about it at all. This means that anyone is allowed to hold a copy of the public key and use it to encrypt data. The private key must always remain a secret. This means only the owner of the private key will ever be able to decrypt the data that was encrypted by its mathematically related public key. This is a very popular visual aid for understanding asymmetric encryption. Let's say Ali wants to send a message to Boba. In such a situation, we need Boba to create a secret key and an open padlock. Only Boba is ever allowed to have the secret key, hence the secret key is analogous to a private key. The open padlock can be publicly distributed for anyone to use, hence the open padlock is analogous to a public key. Boba pays the postal service to deliver the open lock to Ali. If a bad actor intercepts the open lock while it is in transit, there is nothing important to steal. When Ali receives Boba's open lock, Ali places her message into a box and locks it with Boba's lock. Ali then pays the postal service to deliver the box to Boba. If a bad actor intercepts the locked package while it is in transit, the bad actor does not have a key to open the box and read Ali's message. When Boba finally receives the package, only Boba has the secret key to open the lock to read Ali's message. As you can see, a secret key was never shared between any parties in this process, which is what makes asymmetric encryption more secure than symmetric encryption for internet applications. To make this more clear, I will demonstrate a simple mathematical formula that highlights the asymmetric features of asymmetric encryption. Notice these two formulas. One is for encryption and one is for decryption. Notice that they are exactly the same formula, but whether you encrypt or decrypt the message only depends on whether you are using the public key or the private key. Let's define each variable in this equation. The modulus can be any large number. The larger the number you select, the more room you will have for creating a message, because the message must be any number less than the modulus. For the public key and private key, you must select a number for each such that it satisfies this equation. Multiply the public key and private key together, then modulo the product by the modulus. The result must always be equal to 1. Modulo means get the remainder after dividing the modulus into the result of the public key multiplied by the private key. Now, if this sounds confusing, let's just do an example. Let's say our message is the number 2490, and let's arbitrarily pick a modulus of 98,024. Prior to this lecture, I already worked out a pair of public and private key that satisfies this equation when using a modulus of 98,024. The pair is 15 for the public key and 6,535 for the private key. Also, a side note, both the modulus and the public key can be freely distributed because they are not confidential pieces of information. Now, let's encrypt the message. To encrypt our message, we multiply our message with the public key and then find the remainder after dividing by the modulus. So, the message of 2490 multiplied by the public key of 15 gives the number 37,350. The remainder of 37,350 divided by 98,024 is 37,350. This means our encrypted message is 37,350. To decrypt the message, we use the same formula, but this time we use our private key instead of our public key. The encrypted message of 37,350 multiplied by the private key of 6,535 is 244,082,250. The remainder of 244,082,250 divided by 98,024 is 2,490. As you can see, the 2,490 is our original message. And this is a basic example of encrypting and decrypting with asymmetric encryption. This mathematical formula that we just used is only for demonstration purposes and it has no practical value. It is far too easy for a computer to crack the private key. So instead, here on the right, we have two very popular asymmetric algorithms. You will see RSA mentioned quite often. RSA stands for the names of the three people who made it: Ron Rivest, Adi Shamir, and Leonard Adelman. RSA is widely used today. Another one that is gaining a lot of popularity in recent years is elliptic curve cryptography. It is being used as an alternative to RSA because it can achieve similar levels of security with smaller key sizes and is also more performant. With all this said, let's do a practical demonstration of asymmetric encryption with the OpenSSL command. First, we use this command to create a private key. The OpenSSL Gen RSA means we are using generate RSA tools of OpenSSL. The RSA stands for the RSA algorithm that we mentioned previously. We are going to create a private key with a file name entity.key. The private key is going to be 2048 bits long, meaning the private key can be any number in the range of this many numbers. Next, we use the OpenSSL RSA command to derive a public key that is mathematically related to the entity.key. The public key can be saved in many different formats. I will use the popular PEM format and save the public key with the file name entity.pub. And now we are ready to encrypt and decrypt the message. Let's say I want to encrypt the message yummy burrito. I can pass this phrase over to the OpenSSL RSA util command and use the entity.pub public key to encrypt the message and save it as encrypted.txt. You will see a little bit later that the contents of encrypted.txt will be completely unintelligible, and hence it is safe to share the encrypted.txt file over the internet. To decrypt the encrypted.txt file, we use the OpenSSL RSA util command again and pass in both our entity.key private key and our encrypted.txt file. You will see in a moment that the screen will print the decrypted message of Yummy Burrito. So let's actually try this out. Let's run the OpenSSL gen RSA command to create a private key that is 2048 bits long. You can see that it got saved as entity.key. Let's open up the entity.key file and take a look. This private key is pretty long, which reflects the 2048 bits that we specified. We must keep the contents of this file a secret. Now, let's use the OpenSSL RSA tool to generate a public key that is mathematically related to the private key in our entity.key file. We will save our public key as entity.pub in PEM format. And now, when you open up the entity.pub file, you can see the value of our public key. This value can be shared with anyone. Now let's encrypt the text Yummy Burrito with the OpenSSL RSA util command. We will pass in the entity.pub public key file and save the encrypted text to a text file called encrypted.txt. Now, when you open up the encrypted.txt file, you can see that nothing here is intelligible. Finally, let's use the OpenSSL RSA util command with our entity.key private key to decrypt our encrypted text file. And now you can see that our original text, which was Yummy Burrito, is now visible. At this point, we learned the basics of symmetric encryption and asymmetric encryption. Let us summarize what we learned. For symmetric encryption, we use the same key for encrypting and decrypting a message. Symmetric encryption is fast, but its vulnerability lies in the need to share the secret key. For asymmetric encryption, we use different keys for encrypting and decrypting a message. Asymmetric encryption is more secure than symmetric encryption, but asymmetric encryption is computationally more intensive and slow. In the next episode, we will learn how to take the best of both worlds by learning about key exchange algorithms.